In this next section, 40.6, we're going to explain the Bohr hypothesis. Remember, we were using in the last section, 40.5, the hypothesis that the angular momentum had to be an integer multiple of Planck's constant divided by 2 pi, which we call h bar. That's h with a slash through it. This was first done by Bohr, and the answer is why. Well, this was explained by de Broglie, and de Broglie got the Nobel Prize for this work. He made the argument, and he said, well, I have already surmised that the electron should be a wave. How did he do that? You recall that de Broglie looked at the equations which said that E for a photon was equal to h times the frequency, and P was equal to h divided by the wavelength, and we've already covered both of these equations. And this was actually first conjectured by Einstein for the photon. This is for the photon, done by Einstein. This is his incredible work, Einstein's incredible work, where he, in a certain sense, was one of the founders of quantum mechanics, by saying the photon exists only in certain energy bundles. It has a mass of 0. It must travel with a velocity of the speed of light. And if it has a frequency f, it must have an energy that cannot be divided or added to that's proportional to that frequency. And likewise, it has a momentum p, which is given by this equation here. Well, it was de Broglie who said, if this is true, look at these equations, and you notice that over here we have particle-like attributes, energy and momentum, and over here wave-like attributes, frequency and wavelength. So the photon is both a wave and a particle. Well, if that's true for the photon, he said, I conjecture it's true for matter also. So whereas Einstein took frequency and wavelength and computed energy and momentum, de Broglie said, if we take a particle, like an electron, that has energy and momentum given over here, it must have a frequency and a wavelength given by this. Now, once he had said that, you can see something very interesting. If we have a proton, let's just think of the hydrogen atom, and the electron is in orbit, if the electron is really a wave, then this wave must go around, and it must intersect itself in a constructive way, or it will cancel itself out. Now, de Broglie knew this from optics, that because of waves canceling each other out when they interfere with each other destructively, so he made the conjecture. He said the circumference must be equal to 2 pi r. That must be equal to an integer number of wavelengths in order for this to add up. In other words, we could have one wave going around, or 2 waves, or 3 waves, but you always have to have an integer number so that the waves are constructive. But we know what the wavelength is. The wavelength is h over p. Now watch. We have 2 pi r is equal to n times what's lambda. Lambda, remember, these were originally for the photon, but de Broglie is saying this is true for the electron also. This is going to imply that lambda is equal to h over p. So I plug this in up here for lambda and put h over p. Now I divide by 2 pi over here, multiply by p on both sides, and I get r times p is equal to, well, what is r times p? It's going to be equal to n times h over 2 pi. But this is the angular momentum, r times p. So the angular momentum must be an integer times what? Planck's constant divided by 2 pi. So de Broglie derived or explained the Bohr hypothesis that angular momentum had to be quantized. And he said it's as simple as the fact that the wave must interfere constructively with itself. Consequently, we get this quantized angular momentum, and that answers our question. Why did we have this quantization of angular momentum? Because the electron is a wave, and that wave must constructively meet itself.